So as you are getting set up here for your vodcast on carbon-14 dating, the first thing that I'm going to have you do is make sure that your document is set up to take notes. You're going to be drawing pictures and writing. You're going to be doing calculations. So typing is not appropriate today. So regardless of kind of what device you're on, get yourself ready to draw pictures. So you're either going to get set up in OneNote or in Notability or whatever works for you. So pause if you need to, get yourself set up, and away we go. Okay, so carbon dating is a really practical application of radioactive decay. You know, we've talked about how atoms can emit radiation and literally become a different atom. In this case, the carbon in living things is actually an example of a very practical application of how we can use this. So read with me from the top here. Carbon dating is performed on objects containing bits of organic matter, carbon-based substances that were once included in the bodies of living plants and animals. No carbon atoms are alike, not all of them. And so a very small number of carbon atoms, about 1 in every trillion, have 2 additional neutrons, giving them a mass number of 14. So these ideas should kind of be a little bit of review. These different types of carbon atoms are called isotopes. The carbon-14 atoms are unstable and will disappear or decay on their own in time. This fact is central to understanding how carbon dating is used to establish the age of an object. So if you look here, we have our mastodon under how it works at 3 different phases. Here, the mastodon's happy because it's alive. And then the second picture says, oh no, I just died. And in the third picture, it's, oh, I've been dead a really long time. And this is Miss PB having fun with her clip art. Okay, so let's start up here at the beginning of our story, when the mastodon, or really any organism, is alive. So things that are alive absorb carbon-14 in 3 ways. The first way is by breathing. Anytime you inhale, you are taking in bits of carbon into your lungs, and some of those carbon atoms will be carbon-14. The next way that we do it is by eating. And this is regardless of what you eat. Somebody once asked me, well, if I eat a vegan diet, am I still getting carbon-14? Yes. Everything that we eat is carbon-based. So whether you're eating cotton candy or a hamburger or a salad, it's all carbon-based. And so you're getting carbon-14. The last way that you can do it is by drinking something. Water, it doesn't matter. Tea, coffee, soda. That's another way that you can get C14 into your system. Okay, so here's kind of the picture part. When you are alive and you are breathing and eating and drinking, you are taking carbon-14 in at a steady rate. So if here's your body, here again I said this is picture time, what's happening is you are taking in carbon-14. So you are taking in, and we're going to abbreviate it C14 to make it easier for us because we're going to be talking about this a lot. You're taking in C14. Now, what's also happening is you are having C14 decay into, what it decays into isn't particularly important, but just FYI, it decays into nitrogen-14, so it becomes a different element. And the key is that when you're alive, these 2 arrows happen at a steady rate. So you are inputting as much carbon-14 as you are outputting. They're happening kind of simultaneously. And so this is when an organism is alive. The carbon-14 dating comes in handy after the organism dies. So as soon as our little, here I'm going to draw a little X over the eye of our mastodon. Oh, he's dead. Oh no. Our mastodon just died. The second an organism takes its last breath on this earth, something happens. The carbon-14 levels keep dropping, but are not replenished. And so what happens is we have a slow and steady drop in carbon-14 levels. So those are going down. But the carbon that makes up the rest of your body, remember how we said up here that only about 1 in every trillion carbon atoms is carbon-14. Most carbon atoms are carbon-12. So that is the very stable isotope. Carbon-12 in your body stays steady. And so what we have then is, so this is maintaining a steady amount. The carbon-14 levels drop while the carbon-12 levels stay steady. And this is why that comes in handy. Let's go down to our third little guy here. It's been dead a long time. Let's say you are a paleontologist and you dug up this mastodon skeleton and you want to figure out how old it is. You measure two things. Here we're going to have a little graph. You are going to measure the amount of C12. It's the percentage of carbon-12 in the mastodon bones versus the percent of carbon-14. And now what happens is the longer that this animal stays dead, the carbon-14 levels continuously drop. So what's happening is the carbon-12 stays the same, right? This is the stable isotope. It does not decay. Stable, doesn't decay. So this is like a constant against which we can measure other stuff. The carbon-14 percentage in the bones continuously drops. And that is what we can measure. In comparing how much carbon-12 is in some bones compared to how much carbon-14 is in some bones can let us figure out how old something is, approximately, right? So one thing to know is that this does not work on newly dead things. They haven't been dead long enough. Or, I'm going to say long dead, meaning this is not going to help you date dinosaur bones necessarily. But, so this will work for things that have been dead somewhere in like the 50,000 to 5,000 years ago range. So we're not talking about, this isn't going to help you figure out, if you're a CSI investigator, you're not going to date the death of a body from last week using this technique. It also doesn't work with things that have been dead a long time, like dinosaurs who have been dead for millions of years. Okay, so let's see this in action. Next page. This is, we're going to graph the decay of carbon-14. So an interesting thing to know is that the half-life of carbon-14 is 5,730 years. What you are going to do is you are going to get out your calculator. You could also, no, I'm lying. I was going to say get out your phone, but you will need your calculator for some of these problems because you're going to be doing natural logs. So take a moment, get out a calculator, and then follow along here. So it says complete the following table and make a line graph of the data on the chart provided. The result should be a smooth curving line through all points. So what we're going to do is start with this little table up here. I'm going to start this for you and then give you enough so that you know what you're doing. You can finish it and then I'll kind of point you towards the practice problems. So my picture didn't come out all the way here, but this is 100 on the side, 90, 80. We're kind of going down by tens. Your picture should look better than my picture. What I'm going to do though is start up here where it says the decay of carbon-14. I'm going to think about this sample of carbon-14 through time. So for example, if I start here in years from present, at the beginning, like right at the beginning of our story, we'll say that we have 100% of our carbon-14. After one half-life goes by, how much will you have left? Well, 1/2 of 100 is going to be 50%. So we'd have 50% of our original carbon-14 remaining. Now, after 11,460 years, which I'll tell you right now is 2 half-lives, we will have half of 50 left. So we'll have 25% left. And what you're going to do is you are going to fill out the remainder of these boxes following that pattern. You're then going to take that information down onto this graph and plot it. So here we are. I'm going to do the first three for you, or with you. Do it with me. Here we go. The first one, at time 0, 0 is going to be on our x-axis, we'll have 100% of our samples. I'm going to plot up here. That's 100%. And now this is where you have to do a little estimating. This graph, at best, will be an estimate. My next little data point here, when I have 50% of my sample remaining, I'm 5,730 years kind of from my start point. Well, if I look down here, I have a 0, I have 10,000. Here's 5,000. I'm going to take my best guess and make it just a little more than 5,000. And I'm going to be at 50%. So 10, 20, 30, 40, 50. So I'm going to make my next dot right there. There we go. Okay, next point. I'm going to be at 11,460 years. So again, I'm going to make up my best guess. This graph is purely kind of your best guess. I'll say right about there. And let's say that here is about 25%. Now what you're going to do is you are going to finish the rest of these data points up here, finish plotting, and then it says the result should be a smooth curving line through all your points. So you're going to make, basically you're going to make it pretty, right? So you're going to take it, and ideally you should end up, yours will look so much nicer than mine, you should end up with this curving line. That looks awful. That will go through all of the points that you've created, and you'll make it smooth. You're not going to connect the dots on jagged points. You're going to draw a nice smooth line. Okay, so once you do that, I'm going to bop ahead to just show you what you'll be doing next. Now, then you're going to have a chance to apply this graph that you did on the previous page to some real life questions. So questions 1, 2, and 3 are asking about specific kind of real life half-life puzzles that people did, real scientists did, and they used carbon-14 data to do it. So in these, you're going to use your graph to estimate for these 3 questions. I don't need an exact answer. You're going to just take your best educated guess using the picture that you created. Now, for the 4th page, for this last one, this is when you're going to bust out your calculators and show off your fine skills using our formula that we've been working with. Our final amount of our radioactive sample equals the original amount times 1/2 raised to the number of half-lives. And you'll see some of these problems will relate to how much time has gone by. Some of them will relate to how much of a certain substance is left. So the idea here is that this page is calculations. This page is using the graph that you created here to make some educated estimates. All right, once you're done with these and all these problems, there is an answer key at the very end so you can check your work, and then you can begin studying for your nuclear chemistry quiz.